Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to use the point charge relationship KQ over R squared to calculate the electric field for a charge distribution in a two-dimensional type of problem. So in this example, you imagine we've got this charge distribution here, right? It has a length L. Imagine it's positively charged and it has a total charge Q spread out uniformly over the total length L. We're going to try to calculate the electric field a distance A down from one end. Now, some things I'd like to mention here. All right, electric field directions. So here I've assumed that this thing is positively charged. It doesn't make a hill of beans difference whether it's positively charged or negatively charged. The only thing that would change if this object were negatively charged is the electric field would be in the opposite direction. So remember, electric field's direction is defined as the direction of a positive, the force direction on a positive test charge. So basically, we know that the electric field at this point in space is roughly, maybe kind of down and right because this is positively charged. Had that point been negatively charged, we would know the field would be in the opposite direction. But whether that charge is plus or minus doesn't make any difference really in how you work the problem. The only difference is what direction the electric field vector goes in. So again, what we want to do here is we want to be able to apply the following equation. We know that the electric field for a point charge is KQ over R squared, but this is not a point charge. It's a charge distribution. Mathematically, what we can do is break it up into a bunch of point charges. So what we might do here is throw a coordinate system in, and I'm going to go ahead and do that, and I'm going to do this in green. So I'm going to put a coordinate system, an x-axis here, y-axis here. Okay. Now we imagine breaking this charge distribution into a bunch of chunks, and you only need to really worry about one chunk. So I'm going to imagine a little length here, a little chunk, dx. Right? Now, we're going to need the charge on that chunk, dq, which, just like in my previous example, is equal to the charge density, q over L, times dx. If you look in your textbook, you might see something like lambda dx, where, again, that's what lambda is, the linear charge density. All right, now what we do is we draw the electric field vector created by our chunk. So it's important to note, we're talking about the electric field created here due to only this piece, this little chunk of charge, and the electric field is going to be dead away. So that electric field vector, whoops, go back and redo that, is going to be like this. I'm going to go ahead and label that DE. Now, at this point here, this is the point where if this thing were negatively charged, that DE would go in the other direction. Other than that, there's no difference in how these are worked. Now I'm going to write out an expression here. The DE is going to equal KQ over R squared. Now, here's a very important fundamental of these problems. The R that we're going to need is from chunk to point. That is this distance right there. From here to here is x. From here to here is therefore L minus x. So the R squared, I'm going to write an expression out for it. R squared is equal to L minus x squared plus a squared. That's from Pythagorean theorem on this triangle right there. All right, so what we can do is we can write this. The electric field is going to equal K dq, and the Q is equal to Q over L dx, right, over R squared, which can be written L minus x squared plus a squared. All right. Now, this quantity gives the magnitude of the electric field due to this chunk. But we can't just add this. When you're dealing with vector quantities, you cannot just add magnitudes. The only time you could just, get rid of that, add magnitudes is if all the electric fields are in the same direction. But here they're not. The electric field vector here is going to change in direction as our point moves from left to right. All right, so what we're going to do here is we need to add vectors the way we always add vectors, and that's by adding components. So what I'm going to do here is we're going to do separate calculations for the x component of the net electric field and for the y component. So right now I'm going to do the x component. So I'm going to call this dEx. And I'm going to get the x component by taking our electric field and multiplying by the cosine of that angle right there, theta. Now take note that that's the same as this angle. So we've got k dq over r squared. That's the magnitude of the electric field vector. I'm going to multiply that by cosine theta. However, so that I don't introduce another variable into the problem, cosine theta is equal to L minus x over square root of L minus x squared plus a squared. Here's where I'm getting that from. I'm going to go ahead and do this in blue. That's from this triangle right there. The height, this distance is equal to L minus x. This distance is L minus x squared plus a squared square rooted. So cosine theta is this over this, which yields that expression right there. Now, it's a little bit more complex expression, but again, the nice thing is it still only has one variable, x. Had we written that just cosine theta, we either have to convert all our x's to theta or all our thetas to x. This now has this all down to one variable. So now we have an expression for the electric field. Again, k q over r squared, that's our point charge equation, multiplied by cosine theta here picks off the x component. Later on, I'm sure this will get long enough, I'll probably end up doing a separate video, but when we do the y component, what we're going to do is we're just going to multiply that by sine theta, which is equal to a over r. All right, but I'm going to go ahead and just keep working on the x component. So the total electric field, x direction we get by, we have to add all these up. Right, and I'm going to take note that these are constants, so I'll go ahead and just bring those out front. kq over L, and then what we're left with is L minus x dx over, now in the bottom you'll notice that L minus x squared plus a squared, and over here you'll notice L minus x squared plus a squared to the 1/2. These are common things, they can be multiplied. And that's going to multiply to L minus x squared plus a squared to the 3/2. Right? Because this is L minus x squared plus a squared to the first power, and this is the same thing to the 1/2 power. And multiplying those out, we get 3/2 power. All right, so now what we have is an integral expression for the x component of the electric field. Now we got to choose our limits of integration. Because of the coordinate system I put in, the lower limit on x will be 0 and the upper limit L. So 0 to L. So there's our expression for the net electric field. By observation here, I know that this is going to be to the right or the plus I direction. I'm going to go ahead and just tack that on at the end. I think what I'm going to do now is I'm going to pause this and make myself some room and talk about working out the integral. All right, folks, I'm back. So again, what we need to do here, we have this integral expression for the x component of the electric field here at point P, which is right here. That expression needs to be integrated to find total electric field. We've got this expression that we're working with here. I'm going to begin working the integral by making a quick substitution. I guess I got some room up here, so I'll do this up here. I'm going to let u equal L minus x squared plus a squared. I think that will probably get this done. Now when you do an algebraic substitution, first thing we're going to need to do is figure out what du is. Now du, by looking at this expression, is going to equal 2 times L minus x to the first power times the derivative of the inside expression, which is going to be minus 1. The derivative of this is 0 because a is a constant in this problem. Now we got to deal with the limits. If x is equal to 0, then u is equal to, now I'm looking right here, if we put a 0 here, this is going to be L squared plus a squared. If x is equal to L, then u is equal to, and I'm looking right here, That's going to give us a 0 if we put an L right there, so u is going to equal just a squared. So our integral is going to equal kq over L, integral from L squared plus a squared to a squared. And I'll go ahead and just leave this term alone for just a minute. L minus x times dx, which I'm going to look right here to get dx. Whoops, and I forgot that when I did that differential. That last term, that minus 1 dx. I don't think I'm going to go back and remake the video. I'll just take note I caught it right there. Right. So solving this for dx, it's going to equal du over negative 2 times L minus x. So du over negative 2 times L minus x. And then I'm going to come down here. This entire thing now is equal to u. And then that's to the 3/2. All right, equals kq over L, integral L squared plus a squared to a squared. Now you'll notice that these basically cancel. The minus 1/2 can be brought out in front, so I'll go ahead and do that. Boom. And then 1 over u to the 3/2 is u to the, pardon me, minus 3/2 du. And now we can integrate this. So what we're going to do here, let's see, minus kq over 2L. Then antiderivative of minus u to the 3/2. Remember, we have to add 1 to our power. That's going to give us, what, u to the 1/2 minus 1/2. Divide by our new power. That's going to be the same as multiplying by negative 2 over 1. Evaluated L squared plus a squared to a squared. So let's see here. We have this minus 2, minus 2. These are going to cancel. This is going to give us kq over L times the quantity. Now I'm going to evaluate this, u to the minus 1/2 at these limits. Now keep in mind that u to the minus 1/2 means 1 over u to the 1/2 means 1 over square root u. So this is going to be 1 over square root a, which technically, that gives absolute value of a. If if I were grading this and this were an exam and somebody just put 1 over a, I would take that just fine. Minus 1 over square root L squared plus a squared. And this expression gives the net electric field in the x direction. Again, remember, all the way at the beginning of this, this is just dx. Right? So this is our expression for the x component of the electric field. I think what I'll do is just make a completely separate video for the y component. I think the y component has a little more math to it. Some things to take note of here. How do we know when we're right? Well, first thing is this. You always check and make sure these expressions have the correct dimensions. Right? This thing should have dimensions of kq over distance squared. And if you look, this product does. And when we look over here at this product, kq over L, all right, L is a distance. Square root of L squared plus a squared is also a distance. So both products have the correct units, kq over L squared. Another check, I don't have room, and again, the video is plenty long how it is, but another check is this. If we're quite a ways away, this thing should be approximately a point charge. So basically what that means is this. If x is a lot larger than a, then the electric field should be approximately kq over a squared. And it's not too bad to show that here. Find the common denominator and make the approximation that a squared is quite a bit bigger than, whoops, I'm sorry. This was not quite the approximation I wanted. Let me back up. My apologies here. What I meant by that was if a is larger than L in our problem, if this dimension is a lot larger than this dimension, then this thing is approximately a point charge. And then if a is larger than L, when you combine these, you'll find that it will converge to this kq over a squared. So again, this expression is just the x component. I'm going to go ahead and make another video, I think, for the y component. Depending on how long this is, 14 minutes already. Yeah, we're going to make another video here. So we have the x component. Check video 2 for the y component.